Gauss's law chapter. So let me write the problem for you. This time we have an inhomogeneous charge density. It's actually three-dimensional. Rho is the charge density, and it's a function of r. And then some rho 0, which is a constant, 1 minus r divided by capital R. Okay, so here, this is basically a three-dimensional charge density, which only depends on the radial distance, not the angles, not the direction, just the distance from the center, which is r. And it's equal to some constant, and as you can see, when r is equal to 0, rho r is equal to rho 0, right? And then as r increases, then this becomes a smaller number. So this basically is something like, and I have to say this is true when r is less than or equal to r, and rho r is equal to 0, or r is greater than r. So that's basically, you have a charge distribution which is denser at the center, and it gets less and less dense as you go outside, up to a cutoff where this capital R is a constant. Let's say like it's like, I don't know, 10 centimeters. After 10 centimeters, you don't have any charge distribution. So you basically model a dense charge distribution at the center and less dense as you go outside. And the question is, there are two parts of this question. The first part of the question is, look right here, say R, find out the total charge Q in terms of rho 0 and R, and obviously some constants. So that's the first part. And the second part of the question is basically calculate the magnitude of the electric field when R is less than or equal to capital R and R is greater than capital R. For two different situations, let me give them some names. A, when again R is less than or equal to R, and B, when R is greater than R. Okay, so the second part of the question is related to Gauss's law directly, and the first part of the question is finding Q in terms of the other constants which are given in the question. Okay, so let's start with the first part. What is Q? So again, if this charge density had been a homogeneous charge density, what you would do is you would simply multiply the charge density with the volume, right? It's just volume times the density would be equal to total charge. But obviously it's not homogeneous, right? So you can't simply multiply this volume with the density, right? So how are you going to do that? And the idea is the following. It's always this same idea. Take an infinitesimal part of the whole thing and integrate it from from the beginning to the end. So you can think basically the whole thing. Let me draw it with this color. Like, let's say this is capital R. Okay. Start from 0 to capital R. And this sphere, this is a three-dimensional object, this sphere consists of all these small infinitesimal shells of charges, right? Starting from 0 up to capital R. So you basically add them up by means of, obviously this is continuous, so you do it by means of integration, right? And then you get the total charge. So what you want to do is you want to find out, let's say, the charge of this shell, where the radius is R, and the total charge is dq. And you calculate that, and then you basically integrate that to get the whole charge. So the idea, let me write it here, in 3D, this dq is nothing but rho times the infinitesimal volume of this spherical shell, right? And there's an easy way to get this dv, so I need to know this and that. This is obvious, that's this basically homogeneous charge distribution. What is dv for this spherical shell? You can do it by three different ways. One is you can basically take, so this is, so let me draw it. This is, what I mean by spherical shell is the inner radius is R, and the outer radius is r plus dr. Okay, so its thickness of this thing is dr, infinitely small. Okay, you can subtract the inner sphere from the outer one. Right? The outer one has a radius of r plus dr, and the inner one is r. 4 over 3 pi r plus dr cubed, and then you subtract 4 over 3 pi r cubed from that. That's one way to do that. Or you can cut it, open it up, and it's going to look like some rectangular whatever thing, and then you basically multiply the surface of that with the thickness, which is dr. That's another way to do that. The way that I would prefer is taking this as a volume of a sphere, 4 over 3 pi r cubed, and use calculus, right? Just take d of that. These guys are constant, so they will go out. So that's 4 over 3 pi, and inside I have dr cubed. And this is nothing but 3 times r squared times dr. And this 3 and that 3 cancel each other, and you get dv equal to 4 pi r squared dr. Okay, so we are more or less done. We know what rho is, and we know what dv is. And how are we going to get q? Q is all of these dq's, these spherical shells, added up, and from where to where? From 0 to capital R, right? And that is equal to rho, which is rho 0, times 1 minus r divided by capital R, right? The integral is from 0 to r, capital R. And what was dv? It's 4 times pi times r squared dr, okay? And now I can take the constants out of the integral. This is constant, and that's constant. So that would be, so let me change colors. That would be, again, 4 pi is constant, rho 0 is constant from 0 to r. And the first term is it's 1 multiplied by r squared. And the second term is r divided by r multiplied by that is r cubed divided by capital R. Okay guys, so now I have two terms. I have r squared and r cubed divided by r. And this r squared term, the integral, will give me r cubed divided by 3. And the other term will give me r to the 4 divided by 4r. And the integral is from 0 to capital R. Since 0 gives us nothing, it's just 0, it's enough to just put r in here instead of r cubed and r to the 4. The whole thing will look like the following. So it's 4 pi times rho 0 multiplied by the first term will give me r cubed divided by 3, and the second term will give me r to the 4 divided by 4r. This cancels that, and this also gives us cube, right? And r cubed goes out, so that's 4 pi rho 0 r cubed, and I have 1 over 3 here, right? And I have 1 over 4. 1 over 3 minus 1 over 4 is 1 over 12. So that's 1 over 12, and that cancels 4 in here, and I get, this will be my answer here, q is equal to, so that goes away, and I have pi times rho 0, and I have r cubed, and this 4 cancels this 1 over 12, and 3 remains here, right? 3. Okay. That's the charge. Okay, and that's the first part of the question. Now the second part. And we will actually use this. So let's keep in mind, that's all let me put Q in here, that this is the expression, and this will be useful for the second part of the question, as you will see. And what am I going to do? So it's asking us the electric field for these two different regions, R less than or equal to capital R and greater than R. So how do we do it? We basically follow, just Gauss's law. What was that? Let me remind you. It's the electric flux, which is defined as EdA, and if it's a closed Gaussian surface, that's equal to Q inside this Gaussian surface divided by epsilon 0, right? So this is Gauss's law, okay? And what was the idea? So you got to do two things. Let me write it here. This is important. Two things. First one is, you don't want to do this two-dimensional integration or whatever. You want to find a good, in quotations, Gaussian surface, so that you don't have to do the integral, so that E goes out of the integral, so that E in here will go out of the integral. On that surface, at any point on that surface, it's not going to depend on E. You can take it out of the integral. Okay, so that's the first thing that you do. And the second thing that you do, you've got to figure out what this Q enclosed is. So calculate Q enclosed. So more or less all of the Gauss's law questions in this particular type, it's doing these two things. Find a good Gaussian surface, and I define what that good means, right? And then calculate the Q enclosed, use the Gauss equation to figure out the magnitude of the electric field, okay? So let's start with the first one. What is a good Gaussian surface? It's actually obvious from here what a good Gaussian surface is, right? Because if you look at this spherical shell, at any point on the sphere, it is all symmetric, right? Doesn't matter whether I'm here or here, it's all symmetric. And that's why this is a good Gaussian surface. And that's the first part. So we know which Gaussian surface we have to choose. And the second part is, if I choose this particular Gaussian surface with a radius of small r, where r changes, I have to figure out what that enclosed charge is. And I already know what that is from this equation. The only difference will be from the enclosed charge will be the charge inside this sphere, not the whole sphere. So that's why the range of the integral is not going to be from 0 to capital R. It's going to be 0 to some variable small r. Okay, so let's do it. Let's start with the first one. So phi is equal to now the electric field, which goes outside the integral, and inside the integral I just have dA, right? And what is that dA? That's the area of that Gaussian sphere. That's 4 pi times r squared, and that's equal to Q enclosed over epsilon 0. Okay, so I already did this part in here, where I chose this spherical shell, and then I already know how to express and all that. And this Gaussian surface is the sphere with the radius of small r. Remember that this is small r, not capital R, okay? Okay, now, so this is now the magnitude of that, and hence electric field, the magnitude of that is equal to Q enclosed divided by 4 pi epsilon 0 times r squared. So you see, it looks like Coulomb's law, right? The only difference is now what is Q enclosed? Okay, so that's, and I already know that, right? This becomes Q enclosed for r less than or equal to r is equal to this integral, right? 4 pi times rho 0 times all of that. So that's 4 pi times rho 0, integral from 0 to r, with all of that, right? R squared minus r cubed divided by r times dr. This will be, let me change colors, so that's 4 pi times rho 0. I already did that integral here, right? So that's r cubed divided by 3 minus, now it is r to the 4 divided by 4 times capital R. Now remember that the range is from 0 to small r, not capital R. So that's why I'm not going to get this capital R substitution here and then cancellation and so forth. It will remain here. Okay, so therefore, what is the magnitude of the electric field? It is all of that, which is Q enclosed, and there's a nice cancellation here. You see that this 4 pi cancels the 4 pi here, which is good. So I get rho 0, right, times all of this, and let's even make more cancellation. So this r squared is going to cancel 2, and this will become, so this will become 1, and this will become 2. So we will have rho 0 multiplied by r over 3 minus, and from here I'm going to have r squared divided by 4r. And all divided by 4 pi already went away, and that's just epsilon 0, right? Instead of rho 0, I can substitute these guys in here if the question gives us Q, capital Q. So this is equal to, instead of rho 0 from here, rho 0 is 3Q divided by pi times r cubed, right? I can take that and substitute it here. Let's see what it looks like. That's 3Q divided by pi times capital R cubed, and let's put epsilon 0 here, multiplied by r over 3 minus r squared divided by 4r. Okay? So it's either this form or that form. Okay, so that's the answer for the electric field. And obviously, again, this is true when, where do I have that? When r is less than or equal to r, okay? And now the second part, that was A, and let me even put maybe A in here, right? And for B, it's actually simpler because I already know what this Q enclosed is when R, for R bigger than R, the Q enclosed will be, so that this will be the sphere, right, with capital R. And now I'm going to take a Gaussian surface, which is outside where small r is bigger than capital R. Now, again, the same equation is true. So this is the magnitude of E is equal to Q enclosed divided by 4 pi epsilon 0 small r squared. But this time, what is Q enclosed is the total charge in here. I can simply take that and put it in this equation, right? Because inside this Gaussian surface, so this is the Gaussian surface, total charge inside the Gaussian surface is this Q that I already calculated in the first part of the question. So I can just put it here. So let me even give some numbers to these equations. So let's say equation number 1. So using 1, I'm just going to substitute this guy in here. So that will be pi times rho 0 times r cubed divided by 3. So I'm going to put that 3 here. Times 4 pi epsilon 0 times r squared. So there's this nice cancellation of pi's, and the final result will be the magnitude when r is greater than r. That will be rho 0 r cubed divided by 12 epsilon 0 times r squared. Okay?